Okay, we're getting near the end of the semester, so I want to take a few lectures to just practice confidence intervals and hypothesis tests. I kind of feel like those are the two most important things of the class. Everything is sort of building up to those two topics, and so I want to just practice them with you. So we're going to do this problem. Looks kind of long, but I think it's actually going to go very quickly. This is right out of the textbook. Let's read what it says. It says, a sample of 16 small bags of the same brand of candies was selected. Assume that the population distribution of bag weights is normal. The weight of each bag was then recorded. The mean weight was 2 ounces with a standard deviation of 12 ounces. The population standard deviation is known to be 1 ounce. Okay, let's answer these questions. So the first one says, X bar equals what? So you know what X bar stands for, right? That's the sample mean, okay? So what is our sample here? Look, it's a sample of bags, okay? And look right here. The mean weight was 2 ounces. So that's our X bar right there, is 2 ounces. Okay? It says, what does sigma equal? Okay, you know that sigma stands for the population standard deviation. Well, that's told to us right here. The population standard deviation is known to be 0.1 ounces. So that's sigma, 0.1. Okay, next question. What is S sub x? What's that stand for? That stands for the standard deviation of the sample. Here we have that right here. Standard deviation of 0.12 ounces. So that is our X bar, 0.12. Whoops. Okay, so that's the first part, right? Now, in words, define the random variable x. Okay, so what does capital X stand for? Capital X stands for the weight of a randomly selected bag of candy. What is capital X bar? Capital X bar is the mean weight of a randomly selected sample of 16 bags. That's the difference between capital X and capital X bar. Okay, part D. Which distribution should you use for this problem? Explain your choice. Okay, let's write that answer over here. So the distribution we should use is the distribution, remember, it's X bar, comma, that's the mean. It's a normal distribution, okay? So maybe I should write capital N first. A normal distribution with a mean of X bar and a standard deviation of sigma divided by the square root of n. If you know what sigma is, then that's the distribution you should use. Okay, so for us, that's a normal distribution with a mean of 2. and a standard deviation of sigma, which is 0.1, divided by the square root of n, which is 16. Square root of 16 is 4, so that's 0.1 divided by 4, which is 0.025. Okay, it says explain your choice. How do we explain it? That's what I had said before. I gave the explanation first. The explanation is, because we know sigma, then we use the standard deviation, we use the normal distribution with a mean of x bar and a standard deviation of sigma divided by the square root of n. Okay? All right, part E. Construct a 90% confidence interval for the population mean weight of the candies. State the confidence interval and sketch the graph. Those are both parts of question E. They don't have to be done one and then the other. So what we're going to do is we're going to do them at the same time. Okay? So I'm going to start drawing the graph, because looking at the graph helps me to figure out what it is I'm trying to do. So I draw a bell curve. That's a normal distribution. Okay? And we have here right down the middle our mean, which is 2. And they want us to find a 90% confidence interval, which means they want us to break this normal distribution into 3 parts, symmetric around the middle, where the middle part will accommodate 0.90. Okay, that much area, 0.90, that represents a 90% probability. So how much area is going to be in each tail? If it is symmetric and the middle encompasses 0.90, then the tails together must account for 0.10. And since there's 2 tails that are the same size, then each one must accommodate 0.05. Okay? Now, let's find our error bound. Error bound measurement. Okay, remember the formula for that here. We look up on either a table in the back of a book, or we use Excel or something similar. We look up C sub alpha over 2. Alpha here is 0.1. Remember, alpha is a measurement of how much area is out here. That's what alpha is. That means it's 1 minus this number in the middle. Okay? So for us, it's a 90% confidence interval, then alpha is 0.1. Okay? All right, so by the way, I haven't finished writing the formula for the error bound measurement. It's z of alpha over 2 times sigma divided by the square root of n. Okay, so we look this here. Let me get rid of these colors here. Okay, I'm going to leave that purple and green colors. It's not erasing. But in any event, we look up this number in a table or using Excel. Okay, and I did that, and I found. We will go ahead and do. Let's do 3 decimal places. Okay, 1.645. That's what I found for the z-score. Okay? Remember, sigma over the square root of n is already written down on the screen. That's right here. Okay, so 1.645 times 0.025. And that comes out to be, if I can fit it in here, 0. Well, actually, I'm going to just check my work again. 1.645 times 0.025. Yeah, that's correct. I have the right answer. It's 0.0. I just need some more room is all. 0.041125. Okay. So this number right here, by the way, let me point out that error bound in the picture, what that is the distance from the center out to those lines, marking off the middle 90%. Okay, so this guy over here, that is 2 plus 0.04125, and this guy over here is 0 minus 0.04125. Okay, so those numbers are 1.95. Here, again, I just want to double check my work. 0 minus 0.04125. Okay, 1.95875. Okay, and then this one over here is much easier because I can just instantly write down that is 0.04. Oh, sorry, I left out a 1. It's 41125. Let me recalculate that. I had left out one of the ones. So this should actually be 1.95875 and then 0.041125. Okay? And those are the numbers that make up our confidence interval. The confidence interval is the interval from 1.95875 to 2.04125. That's a 90% confidence interval for the weight of a randomly selected bag of candy. Okay? So that's how you do question E. And if you look at this, there's actually not that much to it, is there? I didn't have to write that much. Okay, let's do F. Same exact question, except it says do a 98% confidence interval. And they added this part, calculate the error bound, but that's not additional work because I did that anyways on the last one. Okay, so let's do that, a 98% confidence interval. It's going to look almost identical. Except one thing I can say is now I want the middle section to take up 98% of the area. So that middle section is going to be bigger, which means the tails are going to be smaller. That middle section is going to take up 98% of the area, which leaves 2% left over, broken up into 2 tails. So each tail will represent 1%. Okay, let's do our error bound measurement. Okay, remember our formula. This time, what is alpha? Alpha this time is 2%, so 0.02. All right. Let's see if I have done this one. Yes, I've already looked this one up. Our z-score here is 2.326. If you don't know how to find the z-score, come to my office hours. I can help you. Okay. Sigma over the square root of n is not changed. It's still the same. So 2.326 times 0.025, what do we get? 0.05815. That's our error bound measurement. What's that representing? That's the distance from the center out to each of these lines, marking off the tails. So this one is 2 plus 0.05815, and this one is 2 minus 0.05815. Okay, and that number over there is 1.94185. And the number on the right side is 2.05815. Okay, and that is the two endpoints of our 98% confidence interval for the mean weight, for the weight of a randomly selected bag of candy. Now let's scroll back up and see what the last couple of questions ask for. G says, in complete sentences, explain why the confidence interval in part F, that's this interval, is larger than the confidence interval in part E, which is this one. Okay, and then there's also question H, which means give an interpretation of what this means. So I'm going to answer both of those. Actually, I'm going to answer question H first because that helps explain the answer for question G. Okay, so question H is to give an interpretation of this interval. Okay, and I'm not going to write it out, I'm going to say it. Listen carefully. If I were to randomly select a bag of candy with the intention of weighing it, I am 98% confident that the weight will fall in this interval. In other words, I'm 98% confident that the weight will be somewhere between those two numbers. Okay, now let's answer G. Why is that bigger than this? The reason why is because this interval up here is only a 90% confidence interval. So I want you to think about which of these things is harder to happen. Okay, so you're going to imagine picking a random bag of candy, and you don't even have to pick it up because we're not actually going to weigh it. If I weighed it, then I would know exactly what the weight is. I want you to say, I'm going to imagine picking one out and weighing it, and I'm going to try to figure out what the weight is going to be. Okay, and what if I asked you, give me a range of what you think the weight's going to be, somewhere in what range, okay? And then I told you, now this is important. You don't have to be exactly perfect, but you better be close or else something bad is going to happen. Okay, then you would say, okay, well, how close do I need to be? And if I had told you, I want you to be 90% sure that you are correct. Okay, so you would do that, right? And maybe even you would do this math. And you would say, I am 98% sure that the weight is going to be in this range right here. And I say, okay. Now, what if I told you, you better be 98% sure, and something terrible is going to happen to you if you're wrong, so you better make sure you're right. That means I'm asking you to be more confident in your answer. Well, here, let's use another analogy. What if you were going to shoot a bow and arrow, and I let you pick the size of the target? Okay? If you want to be more confident of hitting the target, then what are you going to do? You're going to make a bigger target, right? A bigger target means you're going to have a higher confidence that you're going to hit the target. That's why this guy's bigger. It's a higher confidence level. I'm only 90% sure that the weight would be in this interval, but I'm 98% sure that it would be in here. How can I be more confident for the second one than the first one? Because the second one's bigger. It's a bigger target. You see how that works? If you wanted a 99% confidence interval, it would even be a little bit bigger than that. So there's really not a lot to these confidence intervals. Some people think, oh man, I don't get this. This is too complicated. And I know it does seem that way sometimes, but look at what's written there. It's actually not that much, is it? They're actually pretty easy to find. It's just a matter of getting the hang of the formulas. All right, I know it wasn't very long, but that's it for today.